Is about the cross product, a review, and equations of planes notes. So just a reminder how to find the determinant of a 2 by 2 matrix. You take 3 times 1 minus 4 times 2, 2 times 3 minus negative 5 times 1. And then when you are finding the cross product of two three-dimensional vectors, you would take 2 by 2 determinants and then multiply it by either ij or k, and the 2 by 2 determinant that you take is, if I'm doing I eliminate the row and column that i's in, and then this ends up being the 2 by 2 I take in order to do that. So here's an example one more time to find the cross product of two vectors. So if I have vector u and vector v, I take u, put it here, I take v and put it here, and then I put ijk up top. If I want to find the cross product, I put I, eliminate the row and column that it's in, then I take the determinant of 3, 5, 2, 3. That's 9 minus 10, so I get negative 1. So negative 1i. And then likewise, I do it for j and k. Remember, you put a minus sign in between here and a plus sign in between here. So I end up with negative 1, negative 1, 1. That is the cross product of u and v. Now, this cross product is a vector. So the dot product gives you a scalar, the cross product gives you a vector, and this vector is perpendicular or orthogonal to both u and v. So it's orthogonal to both of the vectors that you used in order to find the cross product. So it ends up being perpendicular to both of those vectors. Here's another example. Find the unit vector for a unit vector, orthogonal to v and w. So we do the cross product with ijk, 2, 3, negative 1, negative 2, negative 4, 3. We compute all these things, negative 9 minus positive 4, negative 6, negative 6 minus positive 2, which is negative 8, but then you have a negative sign, so it turns into a plus 8. And then negative 8 minus negative 6 gives you negative 2. So here is your orthogonal vector to both v and w. And then we need to find a unit vector, so we divide by the magnitude of this new vector. So our unit vector is negative 13, 8, negative 2, all divided by root 237. So you just find a unit vector the same way you always do, dividing by the magnitude. Now let's say we want to find the equation of a plane. So we use all this stuff that we just learned in order to find the equation of a plane. So in order to find the equation of a plane, basically what I need to do is I need to find a generic vector on the plane. So in order to find a generic vector on a plane, you take some point that is known to be on the plane and then move it in any which way so that it stays on the plane. But in order to make sure it stays on the plane, we have to have a normal vector that is normal to any of these vectors. So if I decided to move x, y, and z over here on the plane instead of where they currently are, so if I decided to move point S over here, n needs to be normal to that one too. So it has to be normal to any vector on the plane. And so how we do that is we know that if we take the dot product of any two orthogonal or perpendicular vectors, we end up getting 0. So if I have some vector x minus x naught, y minus y naught, z minus z naught, where x, y, and z are unknown, but x naught, y naught, and z naught are a point that we know is on the plane, And then I have some known normal vector so that it's normal to the point, to this plane. So if I know this is normal to the plane, and I know that this vector is on the plane, if I take the dot product of those two things, I end up getting 0. So if I compute vector rs, I have x minus x naught, y minus y naught, z minus z naught. I would just dot n and rs and set it equal to 0. So since n is some value which will be calculated, we just take a times x minus x naught plus b times y minus y naught plus c times z minus z naught, and that has to equal 0. And if that happens, then we have a plane. Now, that looks very confusing until you see an example. So we're going to take a 3-step process for writing the equation of the plane. First, if we're given 3 points, we need to create 2 vectors from those 3 points. So that's not too hard. We know how to do that already. Step 2, find an orthogonal vector to both of those vectors. So this will give us a specific normal vector that we know is on the plane. We know that it's perpendicular to the plane because it's perpendicular to the vectors that create the plane. Then step 3, so we use the cross product to do that. And then step 3, we find some generic vector that we know is on the plane with any point that makes it work. And then we dot that with this normal vector we got in step 2 and set it equal to 0. So we're going to have a generic vector with some point that we know on the plane, some generic xyz that will give us all the other points on the plane if we plug stuff in to make it work. Then we dot this and set it equal to 0. So step 1, if I have 3 points, I just find 2 vectors from those 3 points. So I chose hi and ki. Could I have chosen different ones? Yes. I could choose ih, I could choose kh. Any 2 vectors that make the plane will end up working. So you just find 2 vectors by subtracting the points. Step 2, you find an orthogonal vector to both vectors. So we use the cross product. So we've done that a few times. You take the things you get in step 1, you use the cross product with ijk on the top in order to find a normal vector. So this is your normal vector to the plane. So after you do all the work, you get 2, negative 3, 4. You can confirm this works by doing the dot product with both of your original vectors. We already did that in the last video, but I did it in my head, and I know that the answer is 0 for both, so I know that this is a normal vector to the plane. Now I want to use the generic point, or the generic vector that includes a known point from the plane. So you can use any of the 3 known points on the plane, just like you could have used any 2 vectors that are from these points. So when we do the dot product of that, it equals 0, because we know that when we do the dot product of 2 things that are perpendicular, it ends up being 0. So I'll choose k. You could have chosen any one, but I chose k because I don't have any negatives in k, so it's a little easier to do. So I'm going to dot this normal vector with x minus the x value of k, y minus the y value of k, and z minus the z value of k. So this is my generic vector that's always on the plane. So then I do the dot product, 2 times x minus 2, negative 3 times x minus 1, and 4 times z minus 3. Then you simplify, and you get this is the equation of your plane. Let's do another quick example to find the equation of the plane containing these 3 points. So let's find a, b, and ac. So vector ab would be negative 4, negative 1, 9. Vector ac would be 1, negative 6, and 11. So you just subtract those values. Now you need to find the equation of a vector that's normal to this plane. So the normal vector will be ijk. We have to find the cross product with these two vectors. So -4, -1, 9, 1, -6, 11. So if I do I, that would be -11 minus -54. So that's 43. J would be -44 minus 9, which is 53, but -53, but remember we have to change the sign for J. And then for K, it's 24 minus -1. So I end up with 25. If I do the dot product of N and AB and N and AC, or N and any vector up here that I could make from BC or whatever, it should end up equaling 0. And it does. So then what I finally do is I take this vector and I dot it with a generic vector that includes any of these points. So I'll just take A, 3, 5, -2. So that's x minus 3, y minus 5, z plus 2. And the dot product of that has to equal 0 because it's orthogonal with any vector on this plane. 43x minus 3 plus 53 y minus 5 plus 25 z plus 2 equals 0. So 43x plus 53y plus 25z equals 344, and that is another equation of a plane from 3 points.